This video is mainly based on the chapter Path Planning by Potential Field in the book Planetary Exploration by Ellery. Artificial potential fields are mainly used for local path planning and obstacle avoidance, and only rarely for global path planning. Most of the examples and equations I present today are for 2D path planning, but they can also be used or easily adapted for 3D if you want to explore caves, for instance. This video has two main parts. In the first part, I will give you some information about path planning with the potential field method. In the second part, two small and very basic potential field implementations inside a simulator are shown. The basic principle is very easy to understand. Let's take, for example, a simple plane without any obstacles as the environment. We know the robot position and the goal position. Based on the goal position, we create an artificial potential field, which has its global minimum at the goal. Don't get this confused with the terrain. This is completely artificial, but it will represent features of the environment later on. Now we tell our rover to follow a path of potential minimum. We can do that discretely, for example by splitting our environment into a grid and checking the surrounding fields for the lowest potential, or we could for instance check in a certain range for different angles with a certain resolution. This is what I have done in this example. Without any obstacles, the result is a straight line towards the goal. We can also tell our rover to follow a path of potential minimum by taking the negative gradient of the potential field. The result, analog to what you receive when you take the gradient of an electrical potential field, for example, is a vector field. The vector at a certain position then can be seen as the force acting on the robot, pushing it away from obstacles and pulling it towards the goal. This force could be directly used in the control laws of the robot, for example by taking the direction as target angle and the magnitude as the target velocity. Since there are no obstacles, the resulting force vector in every position would point towards the goal. Therefore, the resulting path would be a straight line as well. So let's make things more interesting by adding two obstacles. In this case, to keep it simple, the obstacles are just 2 points. Currently, we think of our robot as a point 2. To take its dimensions into account, we could for example add half of the largest dimension of our robot to the obstacles and keep using this dot representation. As you can see, we will add obstacles by adding high potentials at their position to the potential field. Following a path of potential minimum with the same approach as before, this is the result. You can also imagine the potential field as a mountain range, and when you place a ball at the robot's position and let it go, it will roll down the mountain in a similar path. Depending on how close we want to drive around obstacles, we can make the potential created by the obstacles thinner or thicker. Here we feel rather risky. Here, not so. Also, you can see one problem arising. If we don't limit the influence of obstacles enough, they might shift the lowest potential away from the goal, so keep that in mind. To sum up, we assign an attractive field to our goal and repulsive fields to obstacles. The main advantages the potential field method has are smooth trajectories, if you use the gradient or a discrete approach with a very high resolution, low computational overhead, there are no matrix inversions or other computationally expensive operations, and the ability to cope with dynamic environments. In this picture I added a yellow circle around the robot. This could for example be a laser scanner, and as soon as the laser scanner detects an obstacle, the robot can just add it to the potential field. As a result, the robot will automatically start to avoid the obstacle. There is one major disadvantage when using potential fields for path planning, and that is local minima. Some obstacle configurations, like this U-shaped one, will create local minima. In fact, already two obstacles that are close together with the ideal path leading through the middle of them can be enough to create a local minimum. When the rover drives into a local minimum and checks its surrounding potentials and registers that they are all higher than the potential he is currently on, it will think it reached its goal, which is obviously not the case. So remember, there are obstacle configurations that create local minima, and they are very deadly for path planning when using potential fields. Let's have a quick look at the math. The overall potential field is just an addition of all the attractive fields, this is most of the time just the potential field created by the goal, and all the repulsive fields, namely obstacles. As I said before, the resulting force is the negative gradient of the potential field. When the curl of the derivative is 0, we can also add the forces created by goal and obstacles individually together. This is convenient if new obstacles are detected. Instead of adding the obstacle to the field and recalculating the force, we can just add the force the obstacle creates directly and therefore skip a step. There are some nice things you can add very easily to the potential field or the force. For example, to prevent oscillations, we can add a damping factor that is based on the current velocity. Furthermore, for moving goals, we can take the relative velocities and positions into account for a smooth approach. This might, for instance, be useful for docking with other robots. We have linear scaling factors kp and kv, the relative position and the relative velocity, as well as m and n to control the overall shape of the field. The potential gets low when relative velocity and relative position get minimized simultaneously. Here is an example equation for a goal potential. This potential has linear behavior far away and becomes quadratic close to the goal. The gradient of the potential field gets smaller the closer you are to the goal at the coordinates 4, 6. If we, for example, map the steepness of the field, or in other words, the magnitude of the force, to the robot's velocity, this will lead to a smooth approach because we will decelerate close before reaching the goal. The force at every position can also be calculated fairly easy. The parameter Fgmax influences mostly the maximum force. The limit distance dm controls where the transition between quadratic and linear behavior happens, and kg is a final linear scaling factor. There are a lot of ways to create obstacle potentials. Ideally, we want to represent the obstacle surface as accurate as possible when the obstacle is close to the robot and less accurate, for example with simple symmetric shapes, when it's further away. This makes the computational overhead smaller. As I said before, the potential field method is mostly used for local path planning and obstacle avoidance, therefore we don't care so much about obstacles far away. One fairly common obstacle potential approach that takes the shape, or in other words the surface of the obstacle into account, is called force involving artificial repulsion from the surface, FIRS in short. The obstacle in this example is rectangular. A is just a scaling factor, RO is the effective distance to the obstacle, while R is the distance to the surface of the obstacle. Potential is cut off when it reaches a certain magnitude. It has some nice characteristics. Notice how fast the potential approaches zero after reaching a certain distance from the surface. That prevents shifting around the lowest potential fairly good. Another way to create obstacles is by using superquadratics or superquadrics. With them, basic three-dimensional shapes can be represented. It looks very complicated at first, but if you choose 1 for ax, ay, az and epsilon 1 and 2, you get the basic equation of a sphere with radius 1. If you choose a smaller value like 0.1 for epsilon 1, then the sphere will turn into a cylinder-like shape. If we now choose different values for ax, ay and az, we stretch the superquadratic according to the value in the respective axis. If we now also reduce the value of epsilon 2, we get a box-like shape. When playing around with the parameters, you get a feeling of the primitive shapes you can create with this. The superquadratic can then be transferred into the form we use for the potential. In general, there are a lot of things you can take into account when creating goal and obstacle potentials, like the robot's orientation towards goal and obstacles, as well as the current angular velocity and acceleration, and the linear velocity and acceleration of the robot. As I said before, you should try to limit the area of the obstacle's influence to prevent shifting the lowest potential away from the goal. However, if you limit it too strong, the robot will avoid the obstacle at the latest possible moment, which is also not what you want in most cases. Furthermore, the potentials and their derivatives, so the force field, should be smooth to guarantee smooth trajectories. The equations you choose are heavily dependent on the environment you expect, so how many obstacles are there, how big are they, how close are they together, the movability and size of your rover, the computational power of your rover, and so on. This can get very complex really fast, if you want to have a really good result. So, what can we do against local minima? There are some reflexive recovery procedures like simulated annealing. You can learn about this in another video inside the YouTube playlist Planetary Rovers, Robotic Exploration of the Solar System, on the channel Robotics at University of Würzburg. Moreover, we can play around with the field parameters when we register that we are inside a local minimum. Another very simple approach is to add some noise to the potential field to slightly move the rover around and hopefully get it to move out of a local minimum eventually. These were some things you can do if you're already trapped inside a local minimum. According to the book Planetary Rovers, the usage of superquadratics for obstacle potentials reduces the likeliness of local minima to occur, so this is something to prevent local minima. Lastly, here are some references I used to gather all this information. Now that we learned some of the basics, it's time to have some fun with this. We will simulate two different robots in scenarios using Rust2 and Gazebo. These tools allow to simulate a robot with its sensors inside an environment, so you can test your algorithm before building or buying a real robot. ROS is the abbreviation for Robot Operating System. It is basically a middleware that allows different nodes, so blocks of software with different tasks, to communicate with each other. In Gazebo, you can visualize your robots and environments with 3D models that you can, for instance, create with Blender. Instead of creating my own robot, I will use the Turtlebot free waffle for this first simulation. Turtlebots are robot kits for education and research with open source software. Turtlebot 3 has a 360-degree 2D laser scanner equipped, which is ideal for path planning with the potential field method. In addition to that, it looks really cool and far more prototype-like and less boring than its successor, Turtlebot 4, which looks like a very expensive Hoover to be honest. To be fair, Turtlebot 4 has far better technology equipped. It has more computing power, more precise motors and better sensors and stereo cameras. Let's launch our test environment, consisting of a unit cube, a cylinder with 0.5 meter radius, and a playground. The laser scan of the robot is visualized by the blue beams coming out of the robot. Furthermore, the equipped camera is visualized as a window placed in front of the robot. I implemented a very basic potential field obstacle avoider. 5 times per second, the robot will create a potential field with its goal point and all the obstacles detected by the laser scanner in a range of 2 meters. The robot drives forward with a constant velocity. Based on the potential field, a force vector is calculated. The robot tries to match the direction of the vector by turning in the right direction. When the robot is close enough to its goal position, it stops. This is the trajectory of the robot with the goal being at 4,0. The cylinder, which is slightly blocking the direct path, is drawn into the plot as well. Now let's set the goal to minus 40. The robot will turn at the start and then avoid the cube until it reaches the goal position. Here is a plot showing the detected obstacle points as well as the current potential at this position. The corner of the cube can be seen in both plots. As you can see, the goal potential is just the distance from the goal with a linear scaling factor. The obstacle potentials are created by dividing a linear scaling factor with the distance towards the obstacle. Obstacle potentials that reach a certain height are cut off. The robot reached its goal with this trajectory. The final test of this very simple potential field obstacle avoider will be to set the goal point beneath the tall slide tower. Now it starts to avoid this climbing thing. It finished. Here is the last drawn potential field. You can see where the 4 poles surrounding the robot are inside the potential field. As you can see, even with a very basic implementation of the potential field method, the robot is able to avoid obstacles and reach its goal in a rather easy environment. With some more work, we could create a permanent potential field that consists of all the obstacles on the path and gradually build up a map-like potential field for global path planning, like in this graphic from the book. Moreover, we could add some damping to prevent the robot from oscillating. Furthermore, we could adjust the goal potential field to have a quadratic shape near the goal and map the forward velocity to the created force, to make the approach towards the goal smoother. However, when the environment gets more cluttered, the robot will stumble across local minima way more often. Furthermore, the potential field method lacks skills like the capability to determine if certain rocks can be crossed or need to be avoided. That's why the potential field method is usually not implemented for planetary exploration. The solutions for navigation and path planning present on rovers are usually far more sophisticated and use the input of a great deal of sensors and cameras. Let's try out the potential field method in another scenario. This is a simulated drone in ROS called Hector Quadrotor, developed and maintained by TU Darmstadt. I created a tunnel environment with Blender. Instead of a laser scanner, I equipped the drone with 4 multi-zone ranging sensors, the grey boxes on the drone, with a field of view of 65 degrees. The detected obstacle points can be visualized in a tool called RVIS. The sensor's output is an 8x8 matrix of measured distances. The 4 different sensors are colored differently in RVIS. The white points are the detected obstacle points by the sensor mounted on the front of the drone. The vertical position of the drone is controlled by 2 additional 1D ranging sensors pointing up and down. Every obstacle point creates a repulsive force based on its distance and orientation to the drone. This will create a resulting force in X and Y direction. To push the drone through the tunnel, a constant velocity is added on the drone's X direction. In other words, there is no direct goal, the drone just needs to fly through the tunnel. No potential field is created, the forces just get added directly. Lastly, the drone rotates around the Z-axis based on the calculated forces for X and Y to keep the drone's orientation in tunnel direction. The resulting X-Y trajectory inside the horizontal part of the tunnel environment can be seen here. Smaller tunnels connected to the main tunnel will make the drone drift towards the wall because the repulsive force is smaller there. With some better controllers, the performance could probably be further improved. I hope you got a good overview about the potential field method. Feel free to check out other videos in this playlist if you want to learn more about planetary exploration. Bye!